everybody, and welcome to Echo Live. My name is Anna, coming to you from the Michigan Science Center's Echo Distance Learning Program. Hi, everybody who is joining in already. I see lots of familiar faces starting to pop up in the chat. This is our first recurring Tuesday program of Echo Live. If you've been tuning in so far, we have moved to a new model. We will still be broadcasting to you live on Facebook, Zoom, and YouTube Live every Tuesday and Thursday at 2:30 p.m. Hi to Evan. I see you joining in on Facebook. Hi, Leanne, on a different account. How exciting. Hi, everybody who's joining in so far. If you haven't done so already, you can, of course, introduce yourself in the chat feature of whichever program you are tuning in on. That is your best way to communicate with me throughout this episode of Echo Live, which I am calling Kitchen Edition. Now, we're going to do some kitchen science experiments here today, things that you can try at home using some materials that you probably have laying around your kitchen. But the unique thing about this set of experiments or activities is that these ones are not going to be edible. I promise you that you are not going to want to eat any of the experiments that we put together today. It'll make sense as we go through them together, but let's get started. For the first activity we're going to try, we're going to do a new spin on our activity that we did a few months ago that we called Sink or Float. Now, we did a whole episode dedicated to which types of objects will sink and which types of objects will float in a container full of water. So I've got a big container full of water here, and I have some various objects down here on the table. And my question to you is you can either test your prior knowledge, if you remember some of these items, or you can take a new guess if you weren't present for our last game of Sink or Float. But here are our objects. Let's go through them. I've got a cup full of ice cubes. I've got a regular soda and a diet soda. I have an egg, a ping pong ball, some of these big plastic buttons. And then in this container, I have some miscellaneous objects like rubber bands. You can see I have some plastic pony beads down in there. And then lastly, paper clips. All right, so we've got all sorts of objects here. And I want you to tell me in the chat, give me your hypotheses or your guesses about which objects do you think are going to float. All right, so again, our options are, you're going to tell me which ones you think will float. Type them in the chat. Our objects that you are choosing from are ice cubes, soda, diet soda, ping pong ball, eggs, buttons, beads, rubber bands, and paper clips. Now, I'll give you a moment. There could be more than one answer. There could be one answer. There could be no answer. But I want you to tell me, what is your guess? Which objects are going to float inside our container of water? While I give you a moment to type in those guesses or hypotheses, let's next go over what exactly did we mean by sink or float, right? So you might remember this diagram from our last game of Sink or Float, which talks about buoyancy or buoyant forces. Now, Sir Isaac Newton told us one of our favorite laws, which is for every action, there is an equal and opposite reaction, which works a lot like this force of buoyancy. Now, gravity is always pulling objects down to the ground, even through water. Gravity is always at work when an object has mass. All of the objects I named have mass. Some of them have greater mass or lesser mass than others, and that's something that would cause our object to sink. But that buoyant force is an opposite force from gravity. It is pushing up on our object through the water. When our buoyant force, that upward force, is greater than the pull of gravity, we say that those objects will float. If the buoyant force is less than the force of gravity, that object would sink, like we see over here on the right. So it's represented by the size of these arrows. So in our diagram that says float, right, the buoyant arrow or force is much larger than the force of gravity, and opposite in our sinking side. Now let's see, any good guesses coming in just yet? Let's see. Justin in Zoom says, the banana. What kind of banana? Am I missing something around here? Did I leave my lunch sitting out? I don't see a banana, but a banana could sink or float. We might have to test that on a different episode. Good one, Justin. But Justin also tells us that the ping pong ball, both of the cans of soda, and the ice, those are Justin's hypotheses about which objects are going to float inside our container of water. So let's go ahead and put that to the test. Let's add our objects into some of our various containers. Now, I think this one is pretty fun. So we've got 2 cans of soda here. Justin told us that they will float. Let's go ahead and give them a try. So let's go ahead. We'll try the regular soda here. And would you look at that? Our regular soda sank all the way to the bottom. Let's try it out with our diet soda. Ooh, I may have overfilled my container because we're dripping here, but they're not stacked. Our cans are not stacked. They're both free from each other, but our regular soda sank while our diet soda floats, which means that there must be a difference in their buoyant force. Now, this is an experiment that we tried before on a different episode of Echo Live. We talked about why this is the case. Even though these are both cans of soda and the can is made out of the same material, the liquid inside is very, very different. The big difference between diet soda and regular soda is the amount of sugar. If we go ahead and pull out our cans, we can actually find out how much sugar is in each of these cans just by reading the nutrition label. Now, I'm sure we all do this all the time. I'm sure we read the nutrition label of everything we eat, right? I'm just kidding. I know that I don't always do that, but it's important to do that to understand exactly how this experiment works. In our can of regular soda, the amount of total sugars is 52 grams. 52 grams of sugar in this one can of soda. That is a whole lot of sugar. But let's read our diet soda here. Our diet soda has 0 grams of sugar. So in diet soda, they actually substitute that sugar, which is in regular soda, it's very similar to that granulated sugar you would add into a cake, but they actually substitute it for a sugar substitute called aspartame. Now, the big difference between these 2 cans is their density. So if we think about density, like this diagram here, we see that in an amount of space, density is represented by the amount of stuff or the amount of atoms and molecules packed inside. Our diet soda had less molecules in the same amount of space, which made it less dense than the water. In our regular soda, we had 52 grams of that sugar packed into the same amount of space, which made that liquid more dense or denser than the water surrounding it. So density comes into play and helps determine whether the buoyant force on these different objects is greater or less than the force of gravity pulling them down to the bottom of our container. Let's go ahead and test some more of our objects here. Zoom back in. For this, we don't need such a large container of water, so we'll just scoot that one off to the side. And let's test out some more of our objects here. Let's see a couple more people replying here on Facebook. Lots of people saying that the ping pong ball, Justin said this too, that the ping pong ball will float in water. And you are absolutely right. Ping pong balls are full of air, right? And so that ping pong ball full of air has a much greater buoyant force. Even if I push down on it, it always returns to the surface. All right, let's go ahead. Let's try the egg, because the egg is kind of an interesting one here. Let's go ahead, drop it in. And our egg is more dense than the water around it. Eggs are full of proteins and fat, which causes them to be more dense than the liquid water, and therefore they sink down to the bottom. So if you said the egg, if you did not say the egg, you guys were right. The egg does sink. Let's try some rubber bands. I don't think anyone voted that the rubber bands would float, so let's give that one a try. Oh, but would you look at that? Our rubber bands sink right down to the bottom of the container there. So even though they're made of rubber, which is a pretty porous material, that rubber is more dense than the liquid around it, and it sinks right down to the bottom. We also have these plastic jumbo buttons. And let's see, a yellow one sinks, but our pink one appears to float. Even if I kind of disrupt the air, that one appears to float. Now, plastics can be very different too. Just like if we think about our soda, even though they're both liquids, they had different densities. And even though our plastic buttons are both made out of plastic, plastics can be either more or less dense than water as well. Let's try a couple more objects here. Zoom back in. We also have these plastic pony beads. Let's go ahead and we'll just drip those in there. And our beads, they sink. So I don't think anyone said that the beads would float. So you were correct. Let me just get them to off our button there. Sometimes a little bubble of air gets trapped inside, but it looks like for the most part, the only floating object we had is our button. And if you're familiar with maybe just drinking water at home and you like ice cubes in your drink, right? Ice will float on water, which is actually pretty interesting because we've talked a lot about our states of matter here on Echo Live. And we said that as a general rule, right? As we add heat or energy to our states of matter, those molecules will start to spread out and expand and therefore become less dense, have more space in between those molecules. Water is kind of a funky exception to that rule. Water is one of those very unique substances where it is actually more dense in its liquid state than it is as a solid. There's another good diagram to show us about the density of water in both its liquid and its solid form. Liquid forms what we call a crystalline structure when it is solid. Because of those hydrogen bonds, which are represented by those tiny little dots, when water exists as ice or solid water, it's actually much less dense than water. When water is a liquid, those molecules are flowing past each other and they're actually much closer together, which is why ice will float on water, whereas most other solids will sink. Now, we're going to do an experiment, which is a very easy one for you to try at home, but we are going to try to get these objects that we've sunk in our cup of water to float by changing the density of the water. The way we're going to do that is by adding salt. So we're just going to start adding salt to our water, and we're going to make some observations. Now, as we add the salt, right, we are changing the water's density. When we have substances dissolved in water, right, it becomes more dense. If you think about that diagram, it now has more stuff packed in the same amount of space. It's important that we stir it in, creating our homogeneous mixture, but pretty soon we'll start to notice that some of our objects that originally had sunk to the bottom are going to start to float. So that buoyant force is going to get greater. Keep adding. We've now melted our ice cube on top, so we can't really judge that one anymore. We've melted our ice cube entirely. We're just going to stir and stir and stir. And you can see that we'll let it settle, but our plastic pony beads are starting to almost levitate off the bottom. They're starting to want to creep up towards the top of our glass here. Now you can try this at home with other things besides salt. You can also recreate this experiment with sugar. You could also try it with cornstarch. You can try it with just about any substance that will dissolve in water. So anything that dissolves in water, we normally say is polar. And we've talked about polar versus non-polar, but basically if it can interact with those hydrogen bonds inside the water, it will dissolve, therefore making the water more dense and causing our objects to float up to the surface. Now, it takes a good chunk or a good amount of salt in order to get objects that are very dense to float to the top. So we would have to add a pretty good amount of salt if we want to get that egg to float to the surface. May have added a little too much water to my beaker here. I'm going to try to stir it. I don't want to break my egg, so I'm trying to be very, very gentle. Just trying to get all that salt to dissolve. But if we can't get the egg to float in the salt water, since we're running out of space, I do want to try another substance. Now, in this smaller beaker, I have something that is not water. Although it looks a lot like water, this is actually isopropyl alcohol. So in the isopropyl alcohol, what do you think? Do you think our egg is going to sink or float? You can tell me in the chat. I'm going to take our egg out, just dry it off a little bit here. Tell me what you think. Do you think that the density of our isopropyl alcohol is high enough that the egg will float? Or do you think the egg will sink down to the bottom just like it did inside our salt water here? Go ahead, tell me what you think. Checking on the chat here. Remember that if you have questions throughout the program, you can, of course, ask them in the chat. If you have suggestions or comments, I'm reading those as well throughout the program. A couple of people saying they're, we're not sure. So a couple of people now chiming in. They think, yes, we might be able to get this egg to float in our isopropyl. Let's find out. Unfortunately, the density of isopropyl is not quite enough to get our egg to float, or to get our egg to float to the top, but something interesting does happen with this isopropyl. If I take another ice cube here and I drop it down in our container, you'll see that ice sinks in isopropyl. Even though our ice cube floated when we dropped it in the water, right? The density of isopropyl is less than the density of those ice cubes, that solid water. And so ice will sink in isopropyl while it floats in water. So if you ever think someone's playing a trick on you, and maybe is trying to serve you some isopropyl alcohol, you can test it by dropping down an ice cube. Just kidding. I hope that never happens, because isopropyl alcohol is what we call denatured. So it's actually very, very dangerous to drink isopropyl alcohol. What it does is it actually denatures any sort of proteins that might come in contact with it. If you are trying this at home and you do happen to have some isopropyl alcohol or even vinegar, which will do the same thing, you can try this experiment as well. So even though our egg sank to the bottom, it didn't quite float in our isopropyl here, we're going to try something else. I'm going to crack our egg here, drop our egg down inside the glass, and what we're doing right now is we are actually cooking this egg without the addition of heat. I've been working on another one for about the past half hour, and you can see that I've almost completely, oh, I wish you could see the top a little better. Let me try to stir it up. Our egg is now almost entirely cooked just by sitting down in this isopropyl. Our yolk, even if I were to poke it, is now hard. So if I were to poke this one, right, our yolk would explode. We could turn it into scrambled eggs down there inside the container. But even if I poked this egg, we've completely hardened it because we have denatured the proteins inside the egg. What this does is it actually cooks the eggs without heating them. And Justin said again, do not take it, don't eat anything. Lots of people chiming in, do not eat it. And you are all absolutely right. We said that everything on this episode is probably not food safe. I don't recommend eating any of these things. What we've done is, though, we have cooked or denatured the proteins of our egg. We don't have to do it with cooking, even though that's what's represented here in this diagram. You can see that as it's heated or as it's denatured, those proteins begin to turn white as they uncoil and then cross-link with each other. We've done this using isopropyl alcohol, which we said is not edible. It is not edible because it's very, very toxic to drink. But you could also denature an egg or cook it in vinegar as well. The acidity of vinegar is also enough to denature the proteins of your egg without heating them. A vinegar cooked egg is edible, although I do think it might taste pretty disgusting. All right, so we have another kitchen chemistry experiment to try. This is one that we've tried before, but I want to talk about it in a different aspect. Now, we've done this experiment a couple times on Echo Live. We've talked about mixing baking soda and vinegar. So vinegar, highly acidic, right? We said that is what can cause the proteins in our egg to become denatured or cook them. But we can also use vinegar to create an acid-base reaction when we combine it with baking soda. This is the exact same reaction we get if we were to mix Alka-Seltzer into water. Alka-Seltzer contains both an acid and a base, but we're going to combine them separately. So into this bag here, into just a regular Ziploc bag, I'm going to take 1 scoop of baking soda. Just 1 spoonful here is plenty. And then I'm going to pour in a small amount of vinegar. But we might know what this would look like, but we haven't really talked about what it might feel like just yet. And you can't really feel this over the camera, but don't worry, I have a tool that we can use for observation so that I can kind of prove to you the science behind what's happening. If I take our vinegar and I pour it in, I'm sure you could all guess that our experiment was going to bubble and fizz, just like it did. We've really filled this bag with that carbon dioxide gas that was created during our acid-base reaction. But I said what I'm looking for is how this reaction feels. Now, it feels distinctly very, very cold inside this bag. To tell you or show you how cold it is, I'm going to, of course, use our infrared thermometer. We'll just shake it up and get a good temperature reading here. And you can see that it is about 19 degrees Celsius, which we might also call 66.3 degrees Fahrenheit. And I apologize that my virtual background is acting a little funny in here today, but this reaction is definitely below room temperature. It feels very, very cold. This acid-base reaction is what we call endothermic, meaning that in order for this reaction to go to completion, it needs more energy than what it could get out of our ingredients here. So to get that extra energy, it absorbs heat from the environment in order to form and break the bonds that it needs to create that carbon dioxide gas. Evan said 19 Celsius. We might not use Celsius very often here in the United States. I know we have some friends tuning in from Canada. They're probably a little more familiar with Celsius or the metric system. But 19 degrees Celsius is about 66 degrees Fahrenheit, which is well below room temperature, certainly colder than these ingredients started off at, which is they probably started off around 73 degrees, which is about the temperature inside this room. So we said that is an endothermic reaction. And I used 2 symbols to describe these 2 types of reactions that we're going to try. We said the first is endothermic, and I'm pulling in my arms as I grab heat from the environment, pull it in for my reaction, and then I almost look like I'm shivering, right? Just like we do if we go outside, we usually will kind of keep our arms and legs close to our body, try to conserve our heat. So cold reactions are what we call endothermic. But of course, if we have some reactions that absorb heat, right, we must also have some reactions that release heat. Now, actually, when we dissolved the salt into water, we had an exothermic reaction as well. But regular table salt or sodium chloride isn't extremely exothermic. You can't really feel the difference because it's just not very noticeable. But using a different kind of salt that we call calcium chloride, so we had sodium chloride is for eating, calcium chloride is still a salt, and this is the stuff we actually sprinkle on our roads or on our sidewalk in order to melt ice. Now we said this one must be the opposite, right? So instead of absorbing heat from the environment, we say that exothermic reactions will release heat. They give it away. So as they go to completion, as this salt is dissolved in water, I have a small container full of water here, they will actually release heat energy or kinetic energy into the environment around it, which we observe as this reaction feeling very, very warm. So we'll take about the same amount of calcium chloride as we did baking soda. Again, this is our road salt or ice melt that we use for sidewalks. And we don't even need vinegar for this reaction. We just need water. So we'll go ahead, pour it in, seal the bag, and give it a shake. And you'll notice that this one didn't quite fizz like the other. There was no gas created. Really all we're having is that salt diffuse into the water, but this reaction feels really, really warm. Let's really get that salt to dissolve. And then let's take a temperature reading on this reaction. This reaction reads about 105 degrees Fahrenheit. It is very, very warm, definitely warmer than the temperature of my hands. If you're curious about Celsius, it's about 41 degrees Celsius. So this is significantly above room temperature. Now, don't worry, even though it sounds pretty hot, even though 105 sounds pretty hot, remember that your body is about 98.6 degrees Fahrenheit. And so this is certainly not hot enough that it burnt me or anything like that, but it is extremely exothermic. That reaction feels very, very warm inside my fingers because we are releasing thermal energy or heat into the environment as this salt is dissolved. It is very, very hot. So to review, right, we said endothermic absorbs heat, whereas exothermic, if you spread your arms and legs like a big X, exothermic reactions will release heat. They give it away, and so we feel those reactions as warm. So you probably might be able to ask some of your neighbors, or you might be able to find some of this at home. Calcium chloride is the stuff that we use. You can probably find this at the store, maybe at home. Try these two reactions because feeling them really is the best way to observe this on your own. Now we've got one more reaction to show you that we're going to use another kitchen ingredient, and we're going to use its energy in order to catalyze a reaction. Now, when we say catalyze, it might remind you of another of our favorite reactions that we do here on Echo Live, which we call elephant toothpaste. Now, in elephant toothpaste, we take some hydrogen peroxide, or H2O2, and we rapidly break it down by using a catalyst. The catalyst that we normally use is a salt, pretty similar to calcium chloride, but we call that one potassium iodide. When we do that, it actually rips apart the oxygen molecules, traps it in some fun dish soap and food coloring, and creates a big foamy reaction. If you're curious about how you can recreate that experiment at home, you can actually do it pretty easily. So I have all the materials that you would need right here on this tray. I have some Dawn dish soap, and it's acting funny with my virtual background today, so we'll just turn it around. We've got dish soap to trap our bubbles that will give off from our reaction. We've got some regular strength hydrogen peroxide here, so we don't need the 30% stuff that we normally use for this reaction. We can use the regular 3%, or if you'd like it to be a little stronger, you can buy 6% hydrogen peroxide at beauty stores because people use it for hair. But you can find some hydrogen peroxide to recreate this experiment. We, of course, have a little bit of food coloring, which we'll go ahead and add down to the glass. And then the last thing we need is our catalyst. But I'd like for you to guess what this catalyst is. Now, I'll tell you its scientific name, and let's see if you can figure it out. The scientific name for this catalyst that it's actually going to help us drive our elephant toothpaste reaction to completion is something that we call Saccharomyces cerevisiae. Now I've got an actual picture of this microbe right here. And then I've got this picture over here, which is one of the giant plushy microbes that we have here at the Science Center. It's like a stuffed animal version of this catalyst. Does anyone know what we more commonly call Saccharomyces cerevisiae? Now, don't you all wish you spoke Latin? Because those are some big, long words. Now, I can tell you what these words translate to. These words basically translate to sugar fungus. But that also doesn't sound super familiar, but maybe it's a good hint. Does anyone know what I mean if I were to call this sugar fungus? It's something you probably have at home, something that we would find in our kitchen, right? Because we are doing a kitchen edition here on Echo Live. What do you think I have for a catalyst that we call Saccharomyces cerevisiae? Ooh, some people starting to chime in. People might also know this as bread yeast. So if you have bread in your kitchen, you already have some of this catalyst. I, of course, have it in its liquid form here. So if I go ahead and stop my screen share, I've just taken some of this active dry yeast, which you can buy at the grocery store. You might already have at home. This is the same stuff you would use to create a sourdough starter. I know that's a pretty popular activity since quarantine got started, but you can actually grow your own yeast for bread making by starting with one of these active dry yeast powders. I've just gone ahead and I've added some of it or dissolved some of it in some water. And all we're going to do is use that as a catalyst. Yeast is actually a living thing. We said that we would more commonly call it a sugar fungus. So it is a type of living organism. It's full of energy, and it's actually very easily going to be able to take our hydrogen peroxide and rapidly decompose it down into oxygen gas. So let's go ahead and we will add, I'll put on my safety goggles here just to be extra safe. Shouldn't technically need that because this is a very safe reaction, not using those strong chemicals that we normally use for elephant toothpaste. But we've got 2 beakers here with our hydrogen peroxide, adding in our catalyst in 3, 2, 1. So it doesn't quite happen as rapidly as our strong ingredient reaction, but if you take a look right here, we are creating some foam coming out of our reaction there. This one not quite going off. Maybe didn't add quite enough yeast to my mixture there. Oh, there it goes. Seems like it's bubbling now. We said this is a safe way to do this experiment at home. This one creates a pretty nice foamy mess of bubbles down here in the tray. So if you're going to try this at home, definitely recommend trying it in your sink or over a tray or storage container like I've got here. But it's pretty fun and it doesn't require any sort of dangerous chemicals. So again, it was just hydrogen peroxide, some food coloring and dish soap, and then a little bit of that yeast catalyst. So all things you probably already have at home, might not even need to go out to the store to purchase anything for these. Now we're about out of time for today for this edition of Kitchen Chemistry from Echo Live. If anyone has any questions, go ahead, let me know in the chat. Before we go today, a couple more announcements for you. We are so excited that we are opening to the public this Friday. Now, these Echo Live programs will continue throughout the summer, every Tuesday and Thursday, thanks to the generous support of Ford and Denso. But if you are local to our area, starting Friday, July 10th, you can come visit the Michigan Science Center for free as well. We've been preparing, cleaning, sanitizing, getting everything ready for everyone to come visit us again. So we hope that if you are local, you will come visit us sometime this summer while we are free to the public. If not, of course, we hope we'll see you back here every Tuesday and Thursday all throughout the summer. We've got more episodes of Echo Live planned for you. Paulette will be here, Raul will be back, and we've got some brand new faces for you to meet as well. So we hope we'll see you back here on Thursday. And other than that, I hope you all have a great rest of your day. Let me check. Do I like bananas, Justin? The answer is yes, I do. Bananas are delicious. I would be lying if I said I've never been called Anna Banana. What's the next episode? Thursday, we will be visited by Paulette for another episode of our virtual planetarium. So we hope you'll come by because we have a cool program planned where we are going to look through our solar scopes and get an up close look at the sun as long as the weather is not cloudy. But the weather right now is looking fantastic. I think that we will have a great day to look through our solar scopes, learn a little bit more about our favorite, or at least my favorite star, the sun. And then, of course, visit the Michigan Science Center. Go to our website for more details. You can reserve your free tickets online. All of our registration links are live. We'll see you back here Thursday. Everyone have a great rest of your day.